Welcome to the Mastering Object-Oriented Programming course. This 4-week journey will equip you with the skills to build scalable, reusable, and maintainable software solutions. Let's get started. Object-oriented programming is the backbone of modern software development. It empowers developers to write scalable, reusable, and maintainable code. Mastering OOP is essential for understanding frameworks, APIs, and large-scale systems. Over 4 weeks, this course will take you from OOP fundamentals to advanced design principles and real-world applications. Each week focuses on a specific theme to ensure a comprehensive learning experience. By the end of this course, you will understand key OOP concepts such as encapsulation, inheritance, and polymorphism. You will also explore advanced techniques like design patterns and solid principles, all while gaining hands-on experience through projects. Our approach includes conceptual lessons, interactive exercises, quizzes, and practice days. You will also work on mini projects to solidify your understanding and build real-world applications. This course is designed for beginners starting with OOP, intermediate developers looking to refine their skills, and professionals preparing for interviews or advancing their careers. All you need is a basic understanding of programming, a computer with your preferred development environment, and the determination to learn and grow. Embark on this exciting journey to master OOP. By the end of this course, you will have the skills to create scalable, maintainable, and efficient software solutions. Let's dive in and start learning today. Welcome to the introduction of Object-Oriented Programming or OOP. In this course, we will explore the fundamentals and advanced concepts of OOP, providing you with the tools to write cleaner, more efficient, and modular code. Object-oriented programming is a programming paradigm based on the concept of objects. These objects can contain both data, known as attributes, and methods, which represent the behaviors of the objects. OOP helps us organize complex software systems into smaller, manageable units. With OOP, you can create reusable and maintainable code by modeling real-world entities. So, why should we use OOP? First, it allows us to model real-world entities like cars, animals, and buildings in a way that is easy to understand. OOP also promotes code reuse, modularity, and scalability. When your code is structured properly, it becomes easier to maintain and extend over time, making it a great choice for large and complex systems. Let's now look at the 4 key principles of OOP: encapsulation, abstraction, inheritance, and polymorphism. Encapsulation involves hiding the internal state of an object and only exposing it through methods. This ensures data is accessed and modified in a controlled manner. Abstraction simplifies complex systems by hiding unnecessary details and exposing only essential features. Inheritance allows us to create new classes that reuse the properties and methods of existing ones, promoting code reuse. And polymorphism enables objects to take on different forms, making your code more flexible and dynamic. Now let's compare OOP with procedural programming. In procedural programming, we organize code around functions or procedures. In OOP, we organize our code around objects which combine both data and behaviors. OOP is especially useful when building large systems as it promotes modularity and reusability, while procedural programming can become harder to manage as the system grows. To understand OOP better, let's look at some real-world examples. Imagine a car object. It has attributes like brand, color, and engine type, and behaviors like start, stop, and accelerate. Similarly, if smartphone can have attributes like screen size, battery level, and brand, with behaviors like making calls, sending messages, and browsing the web. These objects are the foundation of OOP. To recap, OOP revolves around four core concepts: encapsulation, abstraction, inheritance, and polymorphism. Encapsulation protects data, abstraction simplifies complex systems, inheritance promotes code reuse, and polymorphism allows objects to take multiple forms. These principles form the basis of OOP and will be explored in more details as we move through the course. Now it's your turn. Pick a real world object and identify its attributes and behaviors. For example, consider a laptop. It might have attributes like brand and processor type and behaviors like start, shut down, and run programs. This exercise will help you connect real world entities to object oriented code. To summarize, today we have introduced the concept of OOP. We have learned about its core principles: encapsulation, abstraction, inheritance, and polymorphism. These principles will help us organize and manage complex code more effectively. In the next lesson, we will dive deeper into each concept. Here's an inspiring quote to wrap up today's lesson. The goal of object-oriented programming is to make software more modular, reusable, and maintainable. When you design your code to be more like the real world, it becomes easier to understand and evolve. This quote emphasizes how OOP makes code easier to work with and extend. Welcome to day 2 of our object-oriented programming course. Today, we will dive into the core concepts of classes and objects in OOP. We will explore how these fundamental building blocks of OOP allow us to model real-world entities and define their behaviors. Let's get started. Let's begin by understanding what a class is. A class serves as a blueprint or template for creating objects. It defines the structure and behavior of an object by specifying its attributes and methods. For instance, consider a car class. It may have attributes such as brand and color, and methods like start and stop. A class is where we define the properties and actions that our objects will have. An object is an instance of a class. When we create an object, we are essentially creating a specific entity based on the class blueprint. For example, using the car class, We can create objects like car 1 a red Toyota and car 2 a blue Honda. Each object holds specific data but follows the same structure defined by the class. Now let's look at the syntax for creating a class. Here's an example of how to define a class in C++. We start by using the keyword class followed by the class name like car. Inside the class, we define public attributes and methods. In this example, the car class has two attributes, brand and color, and two methods, start and stop. These methods define the actions that objects of this class can perform. Once we have our class, creating objects is simple. You just declare an object by using the class name followed by the object name. For example, car, my car creates an object of the car class. After that, you can access the attributes and methods of the object like myCar.start to make the car start. Here's an exercise for you. Try creating a car class, define attributes such as brand and color, and add methods like start and stop. The goal here is to practice using classes and objects. Make sure the methods display a message when called. Let's go over an example solution. In this code, we create the car class with attributes brand and color and methods start and stop. The start method will print a message indicating that the car is starting, while the stop method will display a message that the car is stopping. You can see how we create the myCar object and use its attributes. To summarize, a car is a blueprint that defines the structure and behavior of objects, while an object is a specific instance of a class. The class allows us to define attributes and methods, and objects are created from that class to hold real data and interact with the methods. These are the core concepts that you will use in object-oriented programming. Today, we learned about classes and objects. We saw that a class defines the structure of an object, and an object is a real-world instance that follows this blueprint. We also practiced creating classes and objects in C++ and learned the basic of syntax. Tomorrow we will dive into encapsulation, one of the key principles of OOP. For today's exercise, think of another real-world object and define its attributes and methods. For example, you could create a laptop class with attributes like brand, processor, and RAM, and methods like turn on and shut down. This will help reinforce the concepts of classes and objects. As we wrap up today's lesson, here's an inspiring quote to keep you motivated. The best way to predict the future is to create it. Keep building and keep learning and stay passionate about your journey in programming. Thank you for your time. Welcome to day 3, Understanding Encapsulation in Object-Oriented Programming. In this session, we will explore the key concept of encapsulation, how it benefits our code, and walk through some practical examples. Encapsulation is a fundamental concept in object-oriented programming where we bundle data and the methods that operate on that data into a single unit, which is the class. It helps us hide the internal state of an object and only expose what is necessary to the outside world, ensuring better control and security of data. Access modifiers control the visibility of data within a class. There are three main types: public, private, and protected. Public allows access from anywhere in the program. Private restricts access only to the class itself, and protected allows access within the class and its derived classes. Encapsulation offers several benefits, including data hiding, control over data modification, and flexibility. By preventing unauthorized access and reinforcing validation, we can improve the security and maintainability of our code. To control access to private data, we use getters and setters. Getters allow us to retrieve the value of a private attribute, while setters allows us to modify the value, often with additional checks and limitations to ensure data integrity. Let's look at a practical example, the car class. This class uses getters and setters to control access to the private speed attribute. The setter ensures that only positive values are assigned to the speed, preventing invalid input. Here's the code for the car class. We define a private attribute speed and provide a getter method to access it. This ensures that only authorized methods can modify the speed of the car. Now we implement the setter method. This method checks if the new speed is positive before setting it. If it's not, it shows an error message. This illustrates how encapsulation helps control the flow of data and ensures data validation. Encapsulation brings several advantages, including preventing unauthorized access to sensitive data, simplifying code maintenance, and improving the reusability of components. By isolating the internal workings of a class, we ensure that changes to the internal structure do not affect other parts of the system. Now let's put this into practice with an exercise. Create an employee class with private attributes such as name and salary. Use getters and setters to control access to these attributes and add validation to ensure salary is always positive. Here's the first part of the employee class code. We define the private attributes and provide getter and setter methods for the name attribute. These methods allow controlled access to the employee's name. Next, we add the salary related getter and setter methods. The setter ensures that the salary is positive before assigning it, preventing invalid data from being set. To wrap up, here's a motivational quote by Alan Kay. The best way to predict the future is to invent it. Just like encapsulation helps us control the flow of data in our programs, we have the power to design and shape the future of our projects. Thank you for joining this session on encapsulation in OOP. I hope you now have a deeper understanding of this concept and its importance in writing secure and maintainable code. Happy coding! Welcome to day 4 of our object-oriented programming course. Today we will dive into the essential concepts of constructors and destructors. We will understand what they are, how they work, and why they are crucial in object-oriented design. Let's start with constructors and destructors. A constructor is a special function that is automatically invoked when an object is created. It's used to initialize the object's attributes or allocate resources. On the other hand, destructors are functions that are automatically called when an object is destroyed. Their primary role is to release any resources the object has acquired, such as closing files or freeing memory. Let's explore the different types of constructors. First up is the default constructor. This constructor does not take any arguments and initializes an object with default values. For example, if we have a car class, a default constructor might initialize the car's brand to unknown and year to 2020. Next, we have the parameterized constructor. Unlike the default constructor, this one accepts parameters to initialize the object with specific values. For example, you might create a car object with a specific brand and year, like Toyota and 2023. By passing these values as arguments when creating the object. Now let's talk about the copy constructor. This constructor is used to create a new object as a copy of an existing one. It's particularly useful when you need to pass or return objects by value, ensuring that the new object is a duplicate of the original one, without just copying the pointer to the original one. Destructors are the counterpart to constructors. They are called when an object is about to go out of scope or when it's explicitly deleted. Their purpose is to clean up the resources that the object may have acquired during its lifetime. In C++, destructors are defined using the class name preceded by tilde symbol. Constructors are used when an object is created either as a local variable or when it's dynamically allocated. Destructors are used when an object is destroyed either when it goes out of scope or when it's explicitly deleted by the programmer. These functions ensure that objects are properly initialized and cleaned up. Now let's put our knowledge into practice. For today's exercise, create a class named book with 3 attributes: title, author, and price. Implement a parameterized constructor to initialize these attributes. And don't forget to include a destructor that displays a message when the book object is destroyed. Let's now look at the benefits of using constructors and destructors. Constructors ensure that objects are initialized with valid values, and destructors help manage resources, preventing memory leaks. Together, they make your code more reliable, clean, and efficient. To summarize, constructors are essential for initializing objects when they are created, and destructors help with the resource cleanup when objects are destroyed. These concepts are foundational to object-oriented programming and are vital for writing well-structured, memory-efficient code. That wraps up today's lecture on constructors and destructors. Be sure to practice creating and using constructors and destructors in your own projects to get a deeper understanding. Keep learning, and I will see you tomorrow for more OOP concept. Welcome to day 5 of our object-oriented programming journey. Today, we will dive into static members, understanding how static variables and methods work in OOP and when to use them. Let's start by defining what static members are. In object-oriented programming, static members are variables or methods that belong to the class itself, rather than to individual instances of the class. This means that you can access them directly from the class without creating an object. First, let's talk about static variables. Unlike regular instant variables, static variables are shared across all instances of a class. They retain their value between method calls and can be accessed without creating an object. For example, consider a class that tracks how many objects have been created. The static variable will keep count of all objects created from that class. Now let's move on to the static methods. Static methods can be called directly on the class without the need for an instance. However, they can only access other static members of the class. Static methods are often used for utility functions that do not depend on object-specific data. So, when should you use static members? Static members are useful when you need to track data shared across all instances of a class. For instance, if you need to count the number of objects created, or if you have utility functions that don't depend on the object's state. Let's look at a practical example. Imagine you have a counter class. You want to track how many times a method is called. By using a static variable to store the count and a static method to retrieve it, you can easily achieve this. Static members offer several benefits. They optimize memory usage because the variable is shared across all instances. They also allow for utility methods or data that are common to all objects. For example, tracking the total number of created objects. Now it's time for an exercise. Create a counter class with a static variable that tracks how many times a specific method is called. Implement a static method to retrieve the count and test it by printing the result after multiple method calls. In conclusion, static methods are powerful tools in OOP. They belong to the class rather than individual instances and can help manage shared data or functionality. Static variables are shared across instances, while static methods can be used without creating an object. Use static members when you need shared data or behavior across all instances of a class. Before we end today's lesson, here's a motivational quote. Success is a sum of small efforts repeated day in and day out. Keep practicing and you will continue making progress. Welcome to day 6 of our object-oriented programming course. Today is practice day, where we will focus on solving problems that involve object creation, encapsulation, and constructors. Let's get started and dive into the exercises. For our first problem, we will create a bank account class. The goal is to design a class with methods for deposit, withdrawal, and displaying the account balance. This will help us practice working with class methods and encapsulation. In our bank account class, we will define private attributes like account number, account holder name, and balance. We will create public methods for deposit, withdrawal, and displaying the balance. This is an example of encapsulation where we control how data is accessed and modified using getter and setter methods. Here's an example of how we might implement the bank account class in code. We initialize the class with account details and then we can deposit, withdraw, and display the balance. Notice that we use methods to control access to the balance, ensuring it cannot be changed directly outside of these methods. Next, we will work on another problem where we create a class that has private attributes and provides controlled access through methods. This exercise will further solidify our understanding of encapsulation, which is a key principle of object-oriented programming. In encapsulation, we define private variables within the class, making them inaccessible from outside. We provide public getter and setter methods to allow controlled access. This ensures that our class internal state remains safe and secure from accidental changes. Today we have focused on solving problems involving object creation, encapsulation, and constructors. We have learned how to build classes with private attributes and how to control access to these attributes. Understanding encapsulation is crucial for writing secure and maintainable code. To wrap up, we practiced designing classes with encapsulation, allowing for controlled access to class properties. We also worked on common tasks like deposit and withdrawal for a bank account class. These exercises will help you build strong foundational skills in object-oriented design. In our next lessons, we will continue to build on these concepts and tackle more advanced topics. Welcome to day 7, where we focus on consolidating your understanding of the key concepts covered in week 1. Today's session will be divided into 2 parts, a multiple choice quiz to test your knowledge and a comprehensive recap of the topics we have covered so far. Let's begin with the multiple choice quiz. This quiz will cover the essential topics we have learned during week 1. The questions will test your understanding of what object-oriented programming is, its core concepts like encapsulation, abstraction, inheritance, and polymorphism, as well as the differences between classes and objects. Additionally, you will recall concepts such as constructors, static members, and how to implement encapsulation to protect an object's internal state. Get ready to challenge yourself. Now let's take a step back and review week's, week one's core concepts. We started by understanding object-oriented programming or OOP. OOP models real-world systems, allowing for easier structure and maintenance. It focuses on objects which encapsulate both data and behavior. This week we have seen how OOP helps us organize and manage code effectively. Encapsulation and abstraction are key concepts in OOP. Encapsulation allows us to protect an object's integral state, providing controlled access through getters and setters. This ensures data integrity and security. Abstraction, on the other hand, hides the complex implementation details and exposes only the essential features of an object, making it easier for users to interact with it without worrying about the inner workings. Inheritance and polymorphism take OOP to the next level. Inheritance allows a class to inherit properties and behaviors from another, promoting code reusability. We explored single, multi-level, and hierarchical inheritance. Polymorphism enables objects of different classes to be treated as objects of a common subclass. This concept allows for method overriding and function overloading, making code more flexible and dynamic. Next, we looked at constructors and static members. Constructors are special methods used to initialize objects, ensuring they start with valid data. We also learned about static members, which are shared across all instances of a class. Static variables and methods can be accessed without creating an instance of the class, making them useful for tracking global states like the count of created objects. To reinforce what we have learned, we have a recap challenge for you. Your task is to refactor a poorly designed class by applying the principles of encapsulation and utilizing static members where necessary. Additionally, try creating a real-world system like a library or banking system using the concepts we have covered in week 1. This exercise will help solidify your understanding of how to structure OOP applications. That concludes our day 7 session. Remember, the quiz and recap are designed to help you consolidate your understanding of week's 1 OOP concepts. Take the time to reflect on what you have learned, revisit any areas where you feel unsure, and make sure you are comfortable with the core OOP principles like classes, objects, constructors, and static members. With this solid foundation, you are ready to move on to more advanced OOP topics in the coming weeks.